Greetings, geometry students. I appreciate you finding time to get your notes taken care of. And before we get going, just let me say I do appreciate the number of you that have been trying to take care of your notes responsibilities, even on a Friday night. Several people contacted me, a lot of chatter on Edmodo trying to make sure that people were actually looking at the right video. I really appreciate that dedication. That's a great way to start off your year, staying on top of geometry so that it doesn't stay on top of you. Okay, but this is the video that you're actually supposed to be taking notes on for Tuesday's class. So if you are here, you are in the right place. So let's get started. Okay, I'm going to help guide you through how to do your Cornell notes. So this video may take a little bit longer than usual just because I've got a little bit extra information to explain to you along the way. Okay, let's go ahead and jot down the title here. Okay, having the title is a great way as we are reviewing or hunting down information. We can spot that title and possibly get a good indication about what's going to follow in that lesson, so we know if we need to look in this lesson for a piece of information or possibly a different lesson. Our title for today is Points, Lines, and Planes and Their Attributes. Okay, after you've copied down the title, and if I go too fast on something, all you have to ever do throughout the year is I do tend to talk fast because I'm trying to make the notes as short for you as possible. All you got to do is press the pause button, rewind if you need to, and then press play when you're ready to move on. Okay, our next thing that you need to do for your Cornell Notes format is copy down your objective. And our objective for the day is the student will. Anytime you see that TSW, a lot of objectives start off with the student will. Discern the difference between Euclidean and non-Euclidean geometries and learn the basic geometric structures. Okay, the objective is basically a communication from me to you and also from me to myself that this is what must get done before we can say that this lesson has been properly taught. Okay, so again, the student will discern the difference between Euclidean and non-Euclidean geometries and learn the basic geometric structures. Another piece of information that I am required to provide, but you do not have to write down, is what's called the language objective. A little bit of a communication from me to you that this is what you're going to have to be able to do before you can tell yourself that you have really learned the material. The student will demonstrate mastery of the required vocabulary and concepts by responding to questions involving provided diagrams and hypothetical scenarios. Okay, usually that will come at the end of a worksheet or an assignment, and that demonstration of that mastery can happen there. It can happen on a quiz in a day or two. It can happen on a unit test, but at some point in time you're going to have to master this material. But again, the language objective is not something that we have to copy down. Piece of information that we do have to copy down is the essential question. So underneath the objective that you just wrote down, you're going to write down the essential question. This is a question for you to ask yourself before you move on in geometry. Okay, this should tell you, have you actually got this material down or not? And the essential question for today is, do I understand the difference between Euclidean and non-Euclidean geometries, and do I know the basic structures in Euclidean geometry? Okay, so you should have an objective at the beginning of wherever you have started your notes on your paper. Underneath that, you should have an essential question, and the essential question is something we will revisit at the end of the lesson because it's critical to what we are doing. If you can't answer the essential question for yourself, then you're basically setting yourself up for a lot of difficulty when it comes down to a unit test and especially a semester test. Over on the right side of the page, find somewhere to scribble down the date as well. In case your notes ever get out of order or anything like that, you will know that this lesson was on August 29th, I believe, was when it was assigned in class, and we'll be doing it in class on Tuesday, which is September 2nd. You can put either of those dates, no problem. Sorry, I got another window in your way there. Okay, moving on. Okay, now obviously the objective and the language objective and the essential question all talk about Euclidean geometry, so we'd better know what we're is being referred to when we say Euclidean geometry. And Euclidean geometry, basically by the book, is the study of flat space. Okay, Euclid we'll get to him here in just a second. He is a Greek mathematician. In fact, I'll go ahead and turn that next fact over here. He's a Greek mathematician, and Euclid basically kind of worked in two-dimensional space and in smaller dimensions. That we'll get to that. Euclid really didn't worry about three-dimensional space, and we'll talk about that here more in just a minute. Now, back in Euclid's day, which was a couple hundred years ago, basically there were a lot of people around the world that were working on and developing the concept of geometry. And the problem is they did not have the internet and email and things like that, so they couldn't communicate with each other about what had been discovered or named or things like that. Euclid is the mathematician that is given credit for basically gathering all those ideas together and putting them in one publication, kind of organizing all of the terms, all of the definitions, all of the ideas, and coming up with a singular language that the world now studies in the form of geometry. These books that he did write, collecting all that information, are called the Elements. Okay. Euclidean geometry is constructed upon definitions and undefined terms. Now that actually seems like a little bit of a contradiction because definitions are terms that actually are defined, and then it says undefined terms. So it sounds like it's based upon words that have definitions and words that do not have definitions, and in some cases that's actually true. So it is a little confusing, and rightly so, but we'll talk about that a good bit as we go through the year. Okay, the flip side of Euclidean geometry is non-Euclidean geometry. Now, there are other geometries that are not Euclidean that have arisen in the last, actually just the last few decades. But one of the main types of geometry that has come about is what they refer to as taxicab geometry. Okay, sorry for all the background noise. I've got my daughter and a game and a dog and a cat yapping and stuff like that. So if there's been a lot of noise on the audio, I apologize. Anyway, the idea here is Euclid, his geometry is based upon a perfect world, a perfect situation. And as we well know, our world does not exist in perfect situations or anything like that. So taxicab geometry is a more realistic look at what Euclid was organizing centuries ago. Okay, you're looking at a couple of graphs right there, and you can see you have the same 2 points moving through, and then a line moving through the grid connecting the 2 points. One of them cuts basically directly across the grid. Basically, that's the definition of distance. The shortest distance between any 2 points is a straight line connecting the 2 points. And then over there on the right, you also have kind of a distance between the 2 points. However, this one seems to refuse to cross the open spaces of the grids, stays on the grid lines as it progresses from one point to the other point. And that's actually what these are showing. Okay, the one on the left is the basic definition of distance in the world according to Euclid, that you can get off of the grid lines, you can cut through open space, nothing blocks your path going from one point to another point. In taxicab geometry, the idea is a little bit more in the real world type setting. Okay, and that's kind of why they call it taxicab. The idea that if you were to get in a cab and go from one point to another point, you would not be able to jump off of the roads, drive through houses and buildings and over cliffs and things like that to get from one point to the other. You're going to have to stay on the road. You're going to have to dodge objects that are going to be obstructing your path. Okay, and that's basically the idea of distance. It may actually be a longer distance by taxicab geometry getting from one point to another point. And that's just kind of the nature of the geometric universe. However, the majority of, or about 99.9% of everything we're going to talk about this year is based upon Euclid's perfect world geometry. We'll talk about the others just enough to get an understanding of what they mean and what they're about. Other than that, everything else is going to be about what Euclid said in his books, The Elements. Okay. Now keep in mind these new terms that are popping up. Remember, in Cornell note format, your new terms and your main ideas and your main topics, they go on the left side of your page, and your supporting points and topics and details go on the right side. Sorry, I should have mentioned that a little bit earlier, but I forgot. I'll try to do better from here on out. Okay, now all things in geometry are built by three basic structures, and those structures would be the points and the lines and the planes. So you might want to write points, lines, planes, kind of all in a grouping over on the left side of your Cornell notes, and then on the right side you might say something like the three basic structures in geometry. All things are built by these three structures, something similar to that. Okay, basic definition. Okay, a point. Anytime you have a new term, that term goes on the left-hand side of the page, and here comes the definition. It is an object that exists in zero-dimensional space. Along with the definition, you have some supporting details. It has no length, it has no width, it has no depth. So those three things also go over on the right side of the paper. But that's why it says it's in zero-dimensional space, because it does not have length, it does not have width, it does not have depth. In fact, the only way we can even view a point is to draw it basically much, much bigger or wider than it actually is in reality, because in reality it has no volume whatsoever. It does not exist in any of those three dimensions. We cannot even see it. When we discuss points, okay, another supporting detail here, the same as we do with all things in geometry, we are going to identify a point by the type of structure that it is and then the name of the item that is in question. So in this case, we are looking at possibly something like this that I just popped up on the screen there in a diagram. Okay, and you would pronounce this point P. Anytime in geometry that we do something, like I said, you identify what type of a structure you have. In this case, we have a point, and then you call it by its name, and all points are named by capital letters. In this case, it is a P, point P. If you need to refer to it in writing, as in responding to a question that is written in, on a paper or anything like that, you do not just write P, you write point P. P is a letter in the alphabet. Until you identify what P actually is, you now have an incomplete and possibly even an incorrect answer. Okay, so identify the structure and then the name of the structure. Okay, the next basic structure in Euclid's Elements is the line. So we have a new term over on the left, and on the right we have a definition. It is an object that exists in first-dimensional space. Okay, supporting point, it has length, and supporting point, it does not have any width or any depth. That's why we say it is in first-dimensional space, because it only exists in one of these three dimensions. Now, once again, we cannot actually perceive a line. We can't look at it and see it with our eyes in three dimensions because it actually does not have any volume. It just has a length. So again, the only way we can actually see it is to draw it much, much wider than it actually is on our paper. But understand the concept that if it doesn't have any width, we can't actually see it. If it doesn't have any depth, we can't actually see it. We just understand the idea. Of course, a line continues infinitely in both directions. That's another supporting point that would go over on the right side of the paper. And it takes at least 2 points in order to construct a line. Now, that's a little bit misleading because actually a line is an infinite collection of points because the line does go in each direction infinitely. Okay, so what we're saying here is if it takes at least 2 points to construct a line, that means we need 2 points that we can identify it by name in order to actually understand or be able to refer to the line. Okay, so if we are looking at something like this diagram that's getting ready to come up, when we discuss lines, again, we're going to call that structure by its name, which is a line, and then you have to name any of the 2 points that are on the line. As I said, a line will have infinite numbers of points, but the points that you can actually see and that are named in the picture, you pick any 2 of them, and that is a way that you can name the line. Okay, so here we have a line in this little diagram. Okay, just kind of scribble it over on the left side of the paper. Okay, and on the left side of the paper, draw your little diagram. You got point A on one side, you got point B on one side, or the other side. Okay, if we are referring to this particular structure out loud, we would say it is line AB. Now, typically we do identify, when we list the 2 points, they are most correctly done in alphabetical order, but it's not necessary. They could have also said line BA, and that would have been equally correct. But again, you do tend to see it in alphabetical order more than other ways. Okay. If we need to refer to it in writing, there's actually a little bit of a shortcut, and you'll find a good bit of that in geometry. We have a lot of symbolic notations. Okay, so if you need to refer to it in writing in order to answer a question or something like that, one way that you can do it is to simply write down the 2 letters that you're going to identify the line by, and you can put them in either order, and we're going to put a little symbol over the top of it. It's a line, and it has arrows going in each direction, just like the real line has extends infinitely in each direction. Yes, you must put the arrows on the top of that, because as we're going to see in another lesson, if you leave the arrows off, you actually just identified something different than a line, and you probably just missed your question. Okay, so it's still pronounced the same, line AB or line BA. Okay, extra definition here, and the term is collinear. Remember, new terms go over on the left side of your paper, and the definition is 2 or more things that exist on the same line. Okay, 2 or more things were to exist on the same line, we would call them collinear. Okay, moving on. Last structure that we're going to look at for today is Euclid's most basic item in second dimensional space, and that is the plane. Okay, so we have a term over on the left side of the page, plane, and the definition is an object that exists in second dimensional space. Okay, so our definition is over on the left, or on the right side, part. Okay, supporting information, it has length and it has width, and it has no depth. So that's why we say it's in second dimensional space. And we cannot actually perceive a plane with our three-dimensional eyes. Okay, it's like trying to look at a piece of paper if you held it up and look at the very edge. Now imagine that the piece of paper actually does not have any depth at all to it. It would fail to exist in our three-dimensional world. So we actually have to have 3 dimensions on an object before we can actually see it with our own eyes. So we have to use our imagine a little bit in order to understand Euclid's 3 basic structures. Okay. In general, a plane continues infinitely in both of its directions, meaning whichever direction its length is going, it's going in both directions that way, and whichever direction its width is going, it's going in both directions that way. It takes at least 3 non-collinear points to construct a plane. Well, there you see. Okay, we've already seen an instance here right now where we came up with a new term a moment ago, which was collinear, and now that term is being used to define or describe a new property or yet another term. And this is where geometry absolutely gets all over people. Okay, if you do not take the time to learn your vocabulary, well, the vocabulary terms that we go over one day, a lot of times those exact words are used to define a new term the next day. And if you didn't learn your vocabulary, now we are using words that you don't know in order to define other words that you will not know. So geometry can get pretty tough on you, especially if you neglect your vocabulary. So make sure you keep on top of it and study. When we discuss planes, we're going to call them by their name, which is sometimes provided inside the plane in one of the corners, or we can name it by any three non-collinear points. And there's that term again, collinear. Collinear means in the same line. If you put non in front of it, that means they cannot be in the same line. Now that definition does get a little confusing, so we're going to take a look at a diagram and get used to that. I will always provide you a diagram when we come up with a new term or a new theorem or anything like that. Okay, so here we have basically what looks like a parallelogram. Inside of our parallelogram, we have 3 points. The points have names next to them. And then we have this strange little letter P that's just kind of hanging around near the bottom left corner of the parallelogram. Now, the parallelogram that you're looking at is actually the plane. Okay, now we've already said that planes go infinitely in both of its dimensions. So technically a plane doesn't actually have edges, but in order to be able to see it in our diagram, we kind of have to draw a box around it to understand that it's actually there. So please understand that a plane will have edges drawn around it, but those edges do not really exist. The plane continues on in all 4 of those directions. Okay, now let's look at the difference between the letters that have points next to them and the letter that does not have a point next to it. The letter that does not have a point next to it, it is inside of the parallelogram, which is the plane, and it does not have a point next to it. This is a name. Whoever put together the diagram is providing us with a name to go along with our diagram, and we can call that plane P. And again, we always name what kind of a structure we have and then the name that goes with it. Plane P is an absolutely acceptable way to describe what we are looking at right there. However, sometimes they don't actually give us those names and things like that, and it's up to us. All we have to do is pick any 3 points that are not in a straight line, and that will actually generate or describe the plane that you're seeing there. So you can call it plane ABC, and once again, there is no specification on the ordering of those points, so it could say plane BCA, BAC, CAB, okay, any combination of 3 points that are not in a straight line. Okay, and we pick up one last new definition there. Just like we had collinear, meaning in the same line, now we have coplanar. If 2 or more things were to exist on the same plane, they would be coplanar. Okay, now that's going to conclude the new material, but don't disconnect me just yet. Sorry that the video took as long as it did. We're at like 22 minutes at this point. Typically, they don't run that long, but typically I don't spend so much time talking about the Cornell notes and things like that. So I will continue to guide you on the Cornell notes for a couple of more videos, and then I will basically take that part of the video away, and I'll just talk to you about the geometry, assuming that you know how to do it. Now, there's one last thing that needs to be done. Okay, you need to write a summary of the material that you just learned. Now, by summary, we're talking about nothing more than a sentence or 2 sentences that kind of summarize for you, for yourself, what it is that this lesson is about. Additionally, if there are questions that you need answered, things I talked about that did not make any sense to you, and you need a little bit of extra explanation on it, go ahead and jot those down. You're not going to remember them by the time you come to class. And then lastly, you should already have the essential question written down. So it's time for you to kind of self-reflect. Do I understand the difference between Euclidean and non-Euclidean geometries, and do I know the basic structures in Euclidean geometry? You may not be totally solid on that question just yet because you haven't done any practice on it, but hopefully by the time we come to class and you get your assignment and you do your work, hopefully the answer to that question for you will be a yes. But if it's not, if it's a no, or it's a maybe, or it's a kind of, then that is your indication right there that you haven't mastered the material and you're going to have to do something more about it in order to stay on top of things. All right, guys, again, I appreciate your patience on waiting for me to get the video out. I apologize for all the technological problems I had that have delayed me until now. However, I will do better in the future on stuff like this. I hope you're having a good weekend, and I'll see you in class on Tuesday.